Chapter 10, Simple Machines. This lecture will help you understand how energy is transferred using simple machines, how to analyze the efficiency and mechanical advantage of simple machines, and to distinguish among the three types of levers. A machine is a device for multiplying force or changing the direction of a force. No machine can put out more energy than is put into it or create energy. It can only transfer or transform energy. Machines can do any of the following. Machines can multiply the force, such as a lever, can change the direction of the force, such as a pulley, and change the speed at which the forces act, such as in gears. The simple machines are the lever, the wheel and axle, the pulley, the inclined plane, the screw, and the wedge, single or double. When discussing machines, we define the effort force, F sub E, as the force applied to the machine, and the resistance force, F sub R, as the force that the machine applies to the object. Work is defined as a force times a distance. The effort distance, D sub E, is the distance over which the effort force is applied. The resistance distance, D sub R, is the distance over which the resistance force is applied. Work must be conserved, so the effort force times the effort distance must equal the resistance force times the resistance distance. This relationship is expressed as the law of simple machines. Most machines make work easier by multiplying the force. Machines never multiply the work. When using a machine, there is always work put into the machine, W sub in, and work the machine puts out, W sub out. In an ideal machine, the work in equals the work out. That is to say, there is no friction. If the mechanical advantage is greater than 1, the machine multiplies the force. If the mechanical advantage is less than 1, machine multiplies the distance. If the mechanical advantage is equal to 1, machine does not multiply either the force or distance. Probably the only thing it does is change the direction of the force. In an ideal pulley system, a woman lifts a 100 Newton crate by pulling a rope downward with a force of 25 newtons. For every 1 meter length of rope she pulls downward, the crate rises A, 50 centimeters, B, 45 centimeters, C, 25 centimeters, or D, none of the above. The answer is C, 25 centimeters. Ignoring friction, the work in must equal the work out. The work in is the effort force times the effort distance. The work out is the resistance force times the resistance distance. Solving for the resistance distance, the distance the load moves is 0.25 meters. The lever multiplies force. You can see in the example of a car jack that a smaller force applied to a longer distance can raise a much larger weight, force, but only by a distance that must be correspondingly much shorter. 30 pounds of input force results in 600 pounds of output force. No process is ever 100% efficient. Some work is lost to friction. Efficiency is how effective a device transforms or transfers useful energy. It is defined as the work done on or the work output divided by the work input, written as a percentage. A machine with low efficiency means that a greater amount of energy is wasted as heat. Some energy is always dissipated as heat, which means that no machine is ever 100% efficient. The ideal mechanical advantage is the largest possible mechanical advantage a machine can have if the machine operated without friction. To find the ideal mechanical advantage of a machine, you take the ratio of the effort distance over the resistance distance. A sailor uses a block and tackle with a mechanical advantage of 5 to raise a 600-pound load 20 feet. How much rope must the sailor pull to raise the load? Ignoring friction, the work in must equal the work out. The work in is the effort force times the effort distance. The work out is the resistance force times the resistance distance. Solving for the effort distance, the distance the rope moves is 100 feet. If the sailor actually needs to exert 160 pounds of force to achieve the same lift, what is the efficiency of the block and tackle? Now friction is not ignored. The efficiency is the work done divided by the work input times 100%. The work done is the resistance force times the resistance distance of 600 pounds times 20 feet. The work input is 160 pounds times 100 feet. Solving, we find an efficiency of 75%. 75% of the effort goes to moving the load, while 25% of the effort is lost to friction. A lever consists of a rigid bar free to turn on a pivot called a fulcrum. A lever improves mechanical advantage by using rotation. For rotations, we consider torques. The work done on the system is the applied torque. We assume for a small instant in time, the work is done slowly, so we can say the net torque must be equal to 0. In a lever, the applied force can be reduced by increasing the distance between the applied force and fulcrum. Archimedes said, with big enough lever, you can move the world. The diagram shows a lever. On the right is the effort force F sub B, a distance S sub B from the fulcrum. The effort force's distance from the fulcrum is called the effort arm. On the left is a resistance force F sub R, a distance S sub R from the fulcrum, and on the opposite side of the fulcrum. This is the resistance arm. The resistance force is usually the gravitational weight of the object. Since net torque must be equal to 0, the torque due to the effort is equal to the torque due to the resistance. The two torques are at an angle which we assume to be 90 degrees. The ratio of the resistance force to the effort force must equal the ratio of the effort distance to resistance distance. There are three classes of levers. In the first class lever, the fulcrum is between the resistance force and the effort force. In a second class lever, the resistance force is between the fulcrum and the effort force. In a third class lever, the effort force is between the fulcrum and the resistance force. A wheelbarrow 1.2 meters long has a 900 Newton load 40 centimeters from the axle. What is the mechanical advantage? What force is needed to lift the wheelbarrow? First sketch the wheelbarrow. The mechanical advantage is the effort arm divided by the resistance arm, which works out to be 3.00. Writing down what we know and the basic equation, we solve the basic equation to form the working equation, looking for the effort force. Substituting what we know gives an effort force of 300 Newton.